Okay, so here's what we were talking about last time. We were talking about integrals. I spent a bunch of time talking about single variable integrals, just to remind everybody of what the point of view to take. What's the definition of an integral, and then how to think about it and why this is important. And I'm not going to go through all that again because it's a long rant. Right, and reminder in case you're curious, I have an extra recording recorded on my YouTube channel in the playlist called Miscellaneous Topics that is entirely about the definition of an integral and why it's important. Right, specifically why it's important to applications. Okay, so anyway. Right, so what is a single variable integral? Well, it's a Riemann sum. It's this thing right here. And that's fundamentally what an integral is, and that's important so that we can have a foot in the door for all of these other applications. I mean, area under graph is nice and all, but mostly it's the other applications that make the fundamental theorem of calculus so valuable to applied fields. Okay. And then once you have a Riemann sum, aka an integral, then the fundamental theorem of calculus is what allows you to compute it. Okay. All right. So we, based on that, decided to sort of copy that idea, and let's see here. So our copy of that idea was motivated by the idea of volume under a graph, which again is just a motivation. What we came up with, though, as a definition of a double integral is this right here. And of course, now you notice that this looks a lot like a single variable Riemann sum. Appropriately sort of adapted to the multivariable setting. So specifically, notice that this is a function of two variables, not one. The size that we multiply it by is an area, not a length. Right? We're adding up over all n squared of the pieces, the subrectangles that we get instead of a mere n subintervals in the single variable case. Okay. Notation highly analogous. Again, I won't go through all that again. But fundamentally, though, this notation is just a shorthand for this. Riemann sums are what we're actually going to be doing business with. And it's very important to sort of remember that all the way through this course. Okay, so let's see some examples of how this is going to come up. Why are we interested in Riemann sums, aka integrals? Here's one example. Maybe I want to compute a mass of a two-dimensional sheet of metal. This is kind of an analog of the one-dimensional rod question, right? But this is a two-dimensional version. We have a two-dimensional sheet of metal, and suppose that I know here's the rectangle AB cross CD, and let's suppose that I have a density function that's given by this, function of position, function of x and y. So here's my picture. And how would I compute the total mass of this? Well, I'd chop it up into a bunch of little pieces, right? On each little piece, the density is approximately constant, and I would argue on that little piece that mass is density times area. Right? Where, by the way, with the understanding that density here is, to be understood as mass per unit area. Okay. And then I would argue algebraically as follows. I would say, look, the total mass is the sum of all the little pieces of mass that you get when you chop up the rectangle into little pieces. That's just the observation that mass accumulates. Mass is an accumulating quantity. And then after that, I would observe that, furthermore, the quantity in question is a product, just like we talked about last time. Specifically, it's a product of some function appropriate to the application, in this case density, times size of the piece. In this case, size is area. Right. And having observed that to this specific application, notice that my result is exactly an integral. This is straight up exactly the definition of a Riemann sum, aka an integral. And so the argument that I'm going to make to compute mass with an integral is like that. And there we go. Now, of course, it remains, how do we compute double integrals? We'll talk about that momentarily. But we have turned an application into a double integral. How are we doing? Is everybody on board? Okay. Now let's talk about notation a little bit, just for, kind of practically speaking, day in and day out. These notations are a little clunky. That's just a lot of pencil strokes and I don't know. Anyway, it's convenient to use integral shorthand as you write this down. And what I mean by that is, notice when we rewrite this Riemann sum as an integral, what I mean by integral shorthand is that, well, that's going to get rewritten as that anyway, right? And kind of, if you will, because that's going to go to that, it sort of, by process of elimination, all of that's going to get rewritten as that. Kind of, right? So let's just go ahead and capitalize on this shorthand convenience as we develop the Riemann sum. And so I'm going to write delta m as a dm, right? And I'm going to write this initial summation as a double integral symbol, right? So this is in practice I'm going to say it's an acceptable sloppiness. It's a very common acceptable, but admittedly a little bit sloppy form of notation, and everybody does it. So I encourage y'all to do this as well. What I emphasize, though, is you got to remember as you're writing this down, you have to remember these are just shorthands for what you're actually saying, which is this, right? Students get confused sometimes and say, "Where's the m axis?" Right? Well, there is no m. That's not what this is. Right? This is a shorthand for delta m, which represents how much mass is there in that little piece, delta A. Okay, so Riemann sums are what we're actually doing. This is just the convenient way to write it. Okay, yeah. Mm-hmm.
Is it the delta m is the same in the derivatives?
Well, there's a bunch to be said there. In this case, it wouldn't really make sense to talk about the derivative of m. Derivative of m with respect to what? Right? So how is m a function of what variables? So it's not. This is another thing that in sort of introductory discussions of single variable calculus, I think very often instructors are a little bit too casual about throwing around things like delta x and delta y and derivatives and integrals, and it's you got to be a little bit more careful with it. What I wish would happen in single variable calculus classes is that when instructors would write integral, I wish they would point out that this business here, it's just notation. It's just notation. This is just a shorthand way to write that. This is what we're really talking about, right? And then if you want to make some sort of comparison, then you can look and see, well, what is that thing, and does it make sense in some other context? But it's a complicated story. Yeah, it's a great question. Thank you for that. Okay. All right, here let's see another example. Let's suppose we want to compute the population of Colorado. I could have chosen Wyoming. I wanted a rectangle. Not a lot of states are rectangles. So let's compute the population of Colorado with given the population density function. So let's suppose I have some function that tells me, in a given location, in the vicinity of a given location, how many people per square mile. Or in this case, just for sort of numerical convenience, the units are going to be thousands of people per square mile. Otherwise, the function would be like insane in Denver. So, okay. So that being said, this is another argument. It's structurally just like the mass argument. In the same way that the total mass is the sum of the little pieces of mass that you get when you chop it up into little pieces. Likewise, the total population of Colorado, it's the sum of the populations of the little pieces of area that you chop up Colorado into. People are an accumulating quantity, you might say. Okay. And then, also likewise, population is population density times area. And don't forget that extra factor of 1,000 because our units of our population density function was thousands of people per square mile. Okay. And again, Riemann sum, again, integral. And again, you can shorthand this by using integral notation throughout the development. Same idea as different notation. Okay, last example. And I'm choosing these examples just to kind of show you the breadth of different kinds of questions that can be dealt with double integrals. This is absolutely not an exhaustive list. There are so many more, right? But I think these are an interesting sort of spread of things that you can compute with double integrals. So let's suppose we have a tube and water is flowing through the tube or pipe or whatever, right? But the water is flowing in a certain way, the way water actually physically flows in a pipe. It does not all move with the same speed. It just doesn't. The way it actually moves is it's moving slower on the edges and faster in the middle. That's just how it works. And you can see this in rivers, right? If you're on the edge of a river, if you stick your finger in, the water is kind of barely moving near the edge, but of course you can just visually look at some log or twig or what that's going following the current in the middle of the river, and it's moving quite fast. So let's suppose that I know the speed of the water as a function of where you are in the cross section. And by the way, the figure here is poor. I should have made this a rectangle because as of this stage I've only defined integrals over rectangles, and so forgive my mistake in the picture here. Pretend that the cross section of this pipe is a rectangle. Doesn't make much difference. Okay. So given where you are in the cross section, suppose I know speed is a function of location. Here the speed is low, here the speed is higher. How would I compute the total of what I'm going to call throughput, right? The flow rate. How much, cubic inches per second, or cubic feet per minute, or, volume per unit time of water. How much water is actually moving through the pipe? Okay. So we have a calculation we can do here. I'm going to take my rectangle and I'm going to slice it up into a bunch of little pieces. Just like I did when I was adding up mass, or I was adding up population. Here I'm going to add up flow rate. And I appeal to your sort of physical intuition. If I want to know the total volume per unit time going through this pipe, that will be the sum of the flow rates through these individual pieces of area. In other words, the volume per unit time going through this piece plus the volume per unit of time going through this piece, etc. You add up all those volumes per unit time, and that's going to give you the total volume per unit time. Right? Okay. All right. So on each individual little piece, volume per unit time, it's a pretty straightforward calculation. I'm going to write down the volume that goes through it in a given amount of time, and then I'm going to divide by the time. Here's the volume. You can see the volume in a given amount of time. This distance here is just speed times delta t. Right? That tells you that distance. This area is, whatever it is. Delta A. And, the total volume in an amount of time, delta t, that volume is the product. Right? It's purple times green. Gives me the amount of volume. And therefore, volume per unit time, the flow rate through that little piece is the volume divided by the time. So flow rate, volume divided by time. Notice the delta t's cancel, and flow rate altogether is speed times area. That's just how the geometry / algebra / physics of that particular situation just happens to work out. And now notice we have then our second requirement intact. We previously agreed that flow rate accumulates. And now we see that on each little piece we have some function times area. And so the Riemann sum that we write down turns into an integral. Or again, if you prefer, in the shorthand, you can write it down like that. Alrighty. So, now, let's talk about how to compute these things. By the way, here's a kind of a strategic chart of what we're doing here. We have a bunch of applications, and these applications all connect to Riemann sums, aka double integrals. Right? And we've seen how a bunch of different applications connect to Riemann sums, aka double integrals. Right? By the way, one of which was the volume question. That was kind of motivated double integrals in the first place. Okay. And the natural next thing to want to do is figure out how do I compute number answers out of these Riemann sums. Okay. All right. So, I am going to, it's going to take me a little while to develop the answer to that question. I'm going to come at it sort of sideways. Going back up to this picture, I'm going to kind of reinterpret volume as an application here. I'm going to think of volume as an application still, but I'm going to put it up here. And I'm going to compute the volume, which, by the way, I already know volume can be computed with a Riemann sum, aka double integral. But I'm going to compute volume in a different way now to get a different kind of expression. And the reason I want to do this is because I want to be able to make a connection there. This is what I really want. That's what I'm hoping for. Okay, is to be able to rewrite Riemann sums. It's just going to be more convenient to see how that works by thinking of it as a new computation of volume. Okay, so anyway, I just want the strategy laid out there first. So here we go. We're going to take volume and we're going to try to figure out how to compute it. Here we go. So let's look at this rectangle, and we're going to look at a graph of a function. And again, we're going to compute the volume under the graph. Here it is. Right, there's that same kind of a surface. How are we going to compute this volume? We've already kind of done the slicey dicey, add up the volumes of the French fries approach. What I'm going to do differently this time is I'm going to instead think of it simply as a sum of volumes of slices. And I'm not going to keep slicing into French fries. So I'm going to think of this, the total volume that I'm interested in. I want to compute the volume of a kind of a loaf of bread, and I'm going to add it up as the sum of the volumes of the slices of bread. Okay. All right. Now, is that something that we can do? I can write down specifically. I can write down, the volume of each slice is area times thickness. Right, this is not that different from, you all remember in single variable calculus classes when you had, I'm sure you remember if you have an area and you rotate around an axis and you want to compute the volumes of the slices, and it's a cross-sectional area times the thickness. And that cross-sectional area, though, the thing that made that approach actually kind of work at the time was that cross-sectional area was a disk. So pi r squared, right? And so you've got an integrand that you can actually work with. Right up to that point, we're doing the exact same thing here. It's area times thickness, just like in volumes of revolution. The difference here is that this cross-sectional area is not a disk. It's not pi r squared. And furthermore, this is not any other sort of what I like to call barnyard variety geometric figure. This is not a cow or a duck, or it's not a triangle or a square. The familiar shapes for which we have formulas for areas. Okay, it is, however, something I can compute an area of because of this argument here. Let's look at this cross-sectional area again. If I look at that cross-sectional area, that cross-sectional area is the area under a curve. And that phrase rings a bell, right? Area under a curve. Oh, area under a curve. Area under a curve is an integral. We can compute that area with an integral. It's going to be an integral now, and we've got to be careful. Integral of what? Well, it's going to be integral of height What is height as a function of, as we go along here, as we go along in that direction? Well, it's going to be as a function of y. As y goes from C to D, right? Height is a function of y. Okay. So what is that function? What is h as a function of y? Well, if you look at the picture, don't forget what we're doing here. We are trying to find this cross-sectional area. It's a cross-sectional area that happens for a particular value of x. It is for that one value of x that I want to know what the cross-sectional area is. Said differently, for the purposes of this calculation, x is a constant. So x is a constant, y is a variable, and for each value of y, if I want to know that height, well, I know x and I know y, and the height is the function f, right? That function f. The function whose graph I'm looking at, right? This surface is a graph of f. So height is f. Everybody happy? Everybody on board? So, there you go. We can piece this all together then. Keep in mind I'm trying to compute the area. The area is area under a curve. Areas under curves are integrals. Integral of what? Well, integral of height, and here's my formula for height. So, that cross-sectional area, just, slicing up the area, Riemann sums, height times base, etc. That cross-sectional area, you can see right here. Oh, do I have that written? Convenient. Yeah, here we go. That cross-sectional area is this integral. Now, I want to point to some specifics in this integral. Remember, the idea is that y is going from C to D. Y is my variable. As y goes from C to D, that's what takes me along this base and gives me the area in question. So, integral is y goes from C to D. The thickness is that little thickness right there. That's delta y. I'm taking my interval from C to D and I'm chopping it up into little pieces. That, of course, I'm going to call delta y because y is the variable that's changing there. Right? So all of that in mind, y is the variable. Y goes from C to D. Height is f. I'm going to say f of y, and now, of course, recognizing, that x is constant, x is given. It's the value of x for which we're computing this cross-sectional area. So that's f of x comma y, and again, it's a little creepy looking when you write this down. Hey, you can't do that. That's a multivariable function. You're doing a single variable integral. Not really a multivariable function. X is fixed. It's only for that one value of x. Right? So x is treated as a constant, thus resulting in f effectively being a single variable function of y, and this is a single variable integral of that single variable function of y. Everybody on board with the setup? Everybody see how this goes together? Okay. All right. Let's see here. Let's put everything together then. The volume is an x integral of cross-sectional area. That cross-sectional area is itself a y integral of f, and putting that integral inside of that integral all together, here's area as the y integral from C to D. Here's volume as the x integral of that cross-sectional area. And we have here a formula then for how to compute that volume. So this is the second computation of volume that I was talking about at the beginning of this section. Okay. Okay, a lot of little details in there, lots to keep track of. You got to remember there's sort of two stages of the calculation, right? And this might be a good part of the lecture to go to the YouTube channel. Go to that portion, maybe listen to it again, make sure you're good on all the little details. Okay. Terminology, by the way, this expression here is routinely called an iterated integral. Iterated integral because there's an integral inside of which there's another integral. To me, I have never really been entirely comfortable with this terminology. To me, the word iteration means that you're repeating the same thing over and over again, which is, in fact, not really what we're doing here. It's an integral of an integral, but importantly, this is a x integral of a y integral. These are not the same things. They're importantly different, both geometrically and computationally in how we're going to treat them. So, anyway, trying to popularize a term, nested integrals. I think that makes more sense because, kind of like Russian nesting dolls. There's an integral inside of an integral. I think that makes a lot of sense. We'll see if it catches on. I'm not optimistic at this point, but anyway, I use both terms. In this class, I'm going to say nested integrals, but again, the more popular, the more common term to say is iterated integral. Okay, all right. Okay, all right, so now reminder, why are we doing all of this? What's the point? Our goal here was in computing volume, in getting a new thing, which, by the way, we can now fill in. This is now iterated integrals. The point to this was not actually so that we can compute volume. The point was to motivate this connection here. Let me highlight. This connection here is what I wanted to motivate. And you can see now what the purpose of that connection is, because I have successfully now written double integrals that I don't know how to compute. I've successfully written them in terms of single variable integrals. These iterated integrals are single variable integrals. It's a single variable integral of a single variable integral. And it's a new way to deal with single variable integrals, but it is, in fact, just single variable integrals. And y'all know how to evaluate single variable integrals. Y'all evaluate single variable integrals with the fundamental theorem of calculus. In this case, because there's two of them, it'll be the fundamental theorem of calculus followed by the fundamental theorem of calculus. And that'll give you a number answer. So this is our little roadmap. This is how, in practice, the way we're going to solve applications goes like this. Step 1, turn your application question into a double integral. That's step 1. We talked several examples of that earlier today. Step 2 is going to be rewrite your double integral as an iterated integral. We just did our first example of that. And now momentarily I'm going to do step 3, which is once you have your iterated integral, crank it out. Actually use the fundamental theorem of calculus twice to get your number answer. So this is the strategy. This is the big picture strategy. Applications are double integrals, or iterated integrals, values. All right. I'm going to sometimes call these phase 1, phase 2, phase 3. The idea is, there is more that we're going to need to say about these steps in this process. Specifically, there's a bunch to say about phase 2. And as we're doing a bunch of stuff in phase 2, I'm just going to want to focus on that alone. And so I'm not going to bother giving you, what's the application relevant to the phase 2 calculus. Who cares? That's phase 1. That's a separate question. Let's assume we have a double integral, and let's compute the iterated integral, find the resulting iterated integral. And then I'm not going to go on to phase 3 sometimes because, again, separate story, and let's just focus on phase 2. Okay. All right. Okay, so now let's, that said, let's get back to where we were. Here we are. Here's our result. Remember, again, the big point is not that I have a new way to compute volume. The big point is that I have a motivation for a new way to compute double integrals. And do be careful, though, when you're looking at this. These variables are playing different roles at different times. While you're looking at the inside integral, for that inside integral, right, y is the variable. So that y there you treat as a variable. It is a variable. But x is a constant for the purposes of that inside integral. Treat it like a constant because it is. Okay. Then, notice everything sort of changes when you're looking at the outside integral. Purpose of that outside integral, notice x is the variable. And what about the y's? Well, you would have already integrated out your y's. I mean, the whole purpose, again, keep in mind, the whole purpose of this inside integral is that this inside integral gives you area as a function of x, just x. Y was a dummy variable for the purposes of computing a as a function of x. Okay. All right, so let's get our hands dirty. Let's compute the volume under this surface. Notice that this surface is a graph. Namely, this function right here is what's giving me height as a function of x and y. Right? So because it's a graph, because we're looking at a graph, that's our function. That is our integrand. And volume is a double integral. Double integrals, we just argued, double integrals are iterated integrals. Let's look at our domain. Our domain says that x ranges from 0 to 1. This says that y ranges from 0 to 1. So there's our bounds on our integral, our iterated integral. Again, integrand, the thing whose graph we're looking at, is this function f, x squared plus y squared. And you write all that down, and here you go. And let's compute. Okay. Quick observation. Notice you can't compute the outside integral first. In order to compute the outside integral, you would need to know the inside integral, which we haven't done yet, right? So unavoidably, you have to go inside out when it comes to evaluating. Okay, so we start with this inside integral. I emphasize y is your variable here. So you're going to treat y like a variable because it is a variable. But that means also you're going to treat x like a constant. And this is where a lot of students mess up. A lot of students have this instinctive reaction, integrals, antiderivatives, and the antiderivative of x squared is 1/3 x cubed. Right? You all have had it drilled into you, and I get this is a good thing, I suppose, right? But that integrals are certain formulas, and anytime you see x squared, it's 1/3 x cubed. Boom. Not here. Here, x is a constant. You treat it like a constant. Its antiderivative with respect to y, being as it is a constant, its antiderivative is constant times y. Just like it was a 4. It's going to feel weird. Right? It's kind of like partial derivatives, by the way. I don't know if you noticed that analogy. In partial derivatives, we treat variables as constants, and it seems too good to be true. Can we? Is it that easy? But yeah, right. So likewise here, it feels like we should have had to do more work to get that antiderivative. But that's what it is. It's fine. Okay. Right. So let's see here. So the antiderivative there is that. The antiderivative of y squared. Now that's with respect to y. So yeah, 1/3 y cubed. Absolutely. Here's another place that I think a lot of students make mistakes. I just want to again try to show you all where the landmines are. A lot of students will just take the 0 to 1 here and just recopy them as 0 to 1 there and proceed and start plugging in those ones and zeros. Kind of like this. But the problem is, very often, it's really easy to get confused if you're not careful, and to see these ones and zeros and plug in, for example, that 1 there and there, but then forget about the fact that that's a value of y, and maybe also incorrectly plug it in there. That's, of course, not what you're doing. Right? So these ones and zeros here, those are values of y specifically. So since the visual reminder of that has disappeared, after you get to this stage, my little superstition is I always write down y equals 0 and y equals 1. I think that will help you not make that oops. You'd be surprised how common it is for students to plug in the values for the wrong variables. Okay, so I urge y'all, please do that. Anyway, that said, you plug in y equals 1, and the expression turns into this. And then you plug in y equals 0, and the expression turns into that. And, multiply now, collect terms, etc. And you get this. So that inside integral is this thing right here, x squared plus 1/3. How are we doing? Is everybody on board so far? We're not done yet. We still have to do the outside integral. Notice it's a function of x only. The y's have disappeared. Well, of course they have. We just plugged in numbers everywhere we saw y's. So we have here a function of x. We're then taking an antiderivative with respect to x. This is straight up, literally 100% Calc 1 at this point. And I'm going to let y'all work out that Calc 1. The answer is 2/3. Yeah? Okay. All right. Okay. Moving along. Now, back to our initial question here. Here's the picture of the volume. Here's the volume sliced up, computing the volume as a sum of slices. Why, you might ask, did I slice perpendicular to the x-axis first? And the answer is, it's slightly easier to draw pictures perpendicular to the x-axis because this is in a plane where the axes are straight up and straight across, and it's just artistically slightly easier. So mathematically, there's no good reason for this. I did not have to do my x slicing on the what I'm going to call first momentarily, x slicing on the outside there. Okay, you could just as well slice first perpendicular to the y-axis and view the volume as a sum of a bunch of these kinds of slices of bread. It works fine. Nothing wrong with that at all. Sometimes this is even a better choice. So I'm going to leave it as an exercise for y'all to work through the details. They're all right here for your convenience in these diagrams, and all the algebras right here in the book. But notice I'm slicing here first perpendicular to the y-axis instead of the x-axis. That means that for the inside integral, x is going from a to b in this case. Y is the variable that's being treated as a constant for the purposes of computing this cross-sectional area. All the roles are kind of reversed. So think through the details, look at the pictures, try to draw the pictures yourself, etc. And here's the nice punchline. That's really good news. But this double integral, on the one hand, you can slice it up. Hang on. On the one hand, you can slice it up the way we did the first time. Notice that for this first slicing, we have x on the outside and y on the inside. Our integrand is f. Well, of course it is. Same f. For the other one, the y slicing is on the outside, and the x slicing is on the inside. And, of course, f is our integrand. Of course it is. Quick observation, by the way. The integrand for the double integral, the integrand for the nested integrals, always the same. No surprise. Okay. So, said differently, you can do these integrals in either order. Do be careful, though, that when you switch the differentials, we call it, right here, the inside differential's gone to the outside differential's gone to the inside. When you switch the differentials, you've got to switch the bounds also. I mean, I hope that's perfectly clear. This right here says that x goes from A to B. So x goes from A to B independent of whether it's on the outside or the inside. Right? So you got to switch the bounds along with the differentials. Okay. All right. This computational example here is morally equivalent If this is just the same thing with the differentials in the opposite order, very quickly I will point out that means that for this inside integral, the inside integral is now an x integral. That means that x is your variable. That means the antiderivative of x squared really is 1/3 x cubed now, because x is the variable. It is y that is a constant. Notice the variable on the outside is the constant, and being as it is a constant, its antiderivative is just itself times the variable x. Everybody happy? Okay. Okay. All right. Everything else is details. Y'all can follow through. Okay. Okay. So, so let's talk about examples other than volume. Now let me go back to our big sort of strategy picture here, which I've made a mess out of. Let me clean up my mess. Okay. So, originally we computed volume with a Riemann sum. The motivation there was I needed to motivate this formula for Riemann sums. Subsequently, I computed volume with iterated integrals. Works just fine. Allows me to get number answers. Very sweet. Okay. So, why do we need double integrals at all? A lot of students have a problem with this point. Let me remind you, we've already addressed part of this question, but I've already made the observation that you can't connect applications directly to volume. That doesn't really make any sense. What's the population of Colorado? Why would that be a volume? That doesn't make it. It's a geometric. That doesn't really make sense, right? People don't equal volume. Okay. Well, there is also a problem connecting most of these applications directly to iterated integrals. It just doesn't make sense if you really try to think it through, right? It works for volumes, but there is something special about the volume application. What is special about the volume application is that it's geometry, and we have extremely well-developed senses of geometry. And in particular, there is this related idea called area, right? And when I'm talking about geometry, and I say, let's take a slice of, when I compute volume, when I'm talking about taking a slice of volume, I can talk about that cross-sectional area. And I need to be able to talk about that cross-sectional area to then motivate the idea that is then an integral that computes the next thing. For other applications, there is no such sort of intermediate concept. So let's suppose I'm computing mass, for example. Let me come down to the application I want to talk about. Where am I? Oh. Here we go. Yeah. Suppose I want to compute the mass. We've already done one of these, and we made the argument previously that mass is computed with a double integral. Right? And now I also know that double integrals can be thought of as iterated integrals, and take your pick. You can either do dx dy or dy dx, whatever. It doesn't matter. Your choice. And I know that this is something that I can compute. Right? But if I were to try to bypass, if I were to get a little too aggressive and say, phooey on this, we don't need that, let me try to motivate directly that mass is an iterated integral. And let's think about what would that argument look like. Well, what would be the first thing I would write down? The first thing I would write down would be something like, mass is, I would need an integral of something times dy. Well, the total mass is what times dy? I don't have that kind of a density. The density that I have is mass per unit area. So if I have mass per unit area as a given, if I multiply mass per unit area times length, I don't get mass. I don't know what I get. I get something weird. That's something that it's a physics concept that we have not thought through. We just don't have that kind of experience and sort of handiness, ability to visualize physical examples. It's just not a thing. Everybody see the problem? Right, so it really is very much a peculiarity of volume specifically that allows us to compute the volume, either as an iterated integral or as a double integral. So I can't do this thing over here. Back to our diagram. Wow, that's really far back. We've covered a lot of pages here. You can't do this. You just cannot directly connect applications straight to iterated integrals. It doesn't make sense. So it is unavoidably a three-step process, right? Since we can't get to iterated integrals any other way through this path, the only option that I have is what we were talking about earlier. I have to, step one, take my application, write it as a double integral because that makes sense about how stuff accumulates. I then subsequently can rewrite double integrals as iterated integrals because of a clever argument we made about volumes, and let me confess, that argument is just for motivational purposes. It's not a rigorous argument. There's a better way to motivate this connection, but it's very algebraic and kind of opaque and mathematician-y, which I'm all for personally, but it's not Math 212 appropriate. And then once you have your iterated integral, then fundamental theorem. So it's critical that we have this three-step process. And on exams, in recognition of how important this is, I need to see the double integral. I need to see that on the page. And I need to then see that you've rewritten the double integral as an iterated integral. I need to see that too. Because not only can you not do that, but you can't just do that either. Right? So both the double integral and the iterated integral are essential intermediate steps in the calculation. All right. Cool. Moving along. Yeah. Okay. Right. So we're good. Okay. So we're done with that section now. But we've got powerful tools at our disposal now, by the way, right? So we can take a tremendous number of applications. We've seen how to turn applications into double integrals. We've seen a bunch of examples of that. Now we've seen how double integrals can be written as iterated integrals. And then we also have seen a couple of examples of how iterated integrals are really just it's fundamental theorem of calculus twice. And be careful about which variable is playing which role, which variable is a constant, which variable's variable, etc. Okay. All right. So powerful tools. Here's our limitation currently. All of our domains so far have been rectangles. And so we can compute the population of Colorado or Wyoming, or there's a bunch of counties out in West Texas that are nice and rectangular as well, right? But you want to compute the population of Florida. That's not a rectangle, and our methods as of the moment don't technically address that. So that's the next thing I want to talk about, non-rectangular domains. Here's what the good news is going to be, is that other than a bunch of technical formalities that are not Math 212 appropriate, all the ideas pretty much the same. Right? So there's going to be one little twist in how we actually compute with non-rectangular domains, but the big concepts are all the same. And so, for example, how do I compute the as a double integral? How do I compute the mass of this rectangle? Well, I slice into a bunch of little pieces, and I add up all the masses. Chop it up, add it up, as I like to say. Okay. If we had a non-rectangular domain, how would I compute the mass? And the big idea is going to be, well, chop it up into a bunch of little pieces and add up those masses of those little pieces. That's it's the same idea. Right? And how you write that down formally, how you make it precise. You move to a lot of trouble to make Riemann sums very precise for rectangles. This is the mathematical sort of sophistication that we're just not going to talk about. But it can be done, and it's exactly what you think. It's just, come on, add them up. Chop it up, add it up. Same idea. Okay. let me give you a working example of how this relates to iterated integrals. So I'm just going to go through a volume calculation again, right? Just so you can see how the slicing process works, and everything else works analogously. This time, instead of having a rectangular domain, let's suppose that my domain is a triangle with these 3 vertices, and I want to compute the volume under the graph of some nice function f. It's just that I want to compute the volume sitting over a triangle instead of the volume sitting over a rectangle. Here's the picture. And, okay, so I have a triangular base instead of a rectangular base, but there is still, if I have my surface up here, I can still look at the part of that surface that's sitting over, directly over my triangular base, and I still have a volume. And I can still compute that volume in several different ways. On the one hand, I can compute that by slicing it up to a bunch of little French fries. Double integral. It's exactly what you think it is. It's all the French fries that make up this particular, package of French fries. And I can also compute that volume as a slice of bread and think of it as the sum of the volumes of all these little slices of bread. Just like if it had been a rectangular base. Yeah. So, strategically, the development's going to go through just like it did for rectangles. There is one little difference. We're getting to the difference. Let's see, where did I write this down? Here we go. Yeah. Here. Okay, I'm just going to write it again. What we're seeing here with this argument here is that the total volume is an integral dx. We're slicing along the x-axis, so we do our x slicing on the outside. Okay. And then let's see here. What do I have on the inside? Well, I have a cross-sectional area. This cross-sectional area here. And how do I compute that cross-sectional area? Well, that cross-sectional area is going to be an integral as y goes from, some starting point to, the ending point there. So this is going to be integral from, I'm going to say y1 to y2 dy. Yeah, everybody good? By the way, don't forget our integrand is always the same. It's just the whatever function you're looking at the graph of. So this is z equals f. So our integrand is f. It's always the same integrand for the double integral and the nested integral. Okay. How is this any different from what we did with rectangles? There's one little subtle difference, and it has to do with these bounds here. These bounds. So specifically, let's look at this picture. Let me zoom in now so we can see a little bit more detail. If you look at this picture, this bound y2, what is that bound? Well, it's this value. You can see it right there. It's the y coordinate of that point, right? Here's the thing. That's for a certain value of x. What if I chose a different value of x? What if I was looking at some value of x over here? For that value of x, this is what my cross-section looks like. Something like that. And the y-bound, corresponding to that point, that's sort of the last value of y. And notice the y-bound is different. Right, so for different slices, you get different y-bounds. Let me say that a little bit differently. For different values of x, you get different y's. Let me say that just ever so slightly differently again. The y-bounds are functions of x. That's the only change. Everything else is exactly the same. But the big change, again, how to break this up as an integral is that these y-bounds are functions of x. Okay. Okay. Now, exactly how is it a function of x? Well, let me go back to the picture. I guess I'll zoom back in. Back to the picture. This y bound is it's the y coordinate of that point. That point, where you sort of run out of space. That's where the volume ends, if you will. So that point determines the upper y bound. Where's that point? That point is on a curve. In this case, it's on this line. That curve has an equation. I can write down the equation for that curve. By the way, this is an easy equation because those vertices were 1 and 1. And so x plus y equals 1. So the way y'all are going to find these bounds is by connecting the dots in the fall. It's always the same way. Bounds are determined by points. Points are on identifiable curves. Curves have equations. Points, curves, equations. That's always the same sort of little flowchart. Okay. And that being said, keep in mind, why am I interested in this equation? Well, I wanted to solve for a particular value of y. So solve for y in that equation. You get 1 minus x, right? So this bound that says y equals 1 minus x. That's what that upper bound is. And that works. You can plug it in. That works for any value of x. Think it through as, you can just see in the equation and in the picture as x increases, you can see these y bounds decreasing. You can see it in the equation too. It's following along as that point does. It's following along that curve exactly as is described by that equation. Okay. All right. So y is 1 minus x is our upper bound. And here we go. So that upper bound, 1 minus x. So on the inner integral, that y upper bound, 1 minus x. What do you think? Any other questions about that? Everybody happy about that? Well, let's talk about the lower bound real quick. What is that lower bound? I guess I got to go back up to the picture. The lower bound, I guess I can just do it off of this picture. So the upper bound, that point, that curve, that equation, etc. The lower bound, here's a point describing the lower bound. It's on this curve, which has a much easier equation. Y equals 0. So in the same way as we had to solve for y and the equation of the other line, and whatever I solved for y was, well, that's my y bound. For the lower bound, solving for y is trivial. It's already solved for. And you get just 0. So that lower bound for this, in this example, this lower bound is always 0. Everybody happy? Okay. So yeah, lower bound is y equals 0. All right. So everything else exactly the same. And basically, we just have a bunch of examples to plod through for this kind of thing. You know what? Let me talk about the algebra real quick before we go on to other examples. The algebra here, it remains that the inside variable here. So y is the inside variable. That when you're plugging in, you should, just as a little visual reminder, don't forget that's what you're plugging in for. That these numbers here, or these things, these bounds are what you're plugging in for y, right? But notice that they are now functions, right? There's 1 minus x. It's no longer a constant, it seems. And again, this is another sort of really unsettling. Students get, are you allowed to do that? Can you put functions in bounds? Is that legal? What? But let me just remind you, it's not a function, technically, from a certain point. For the purposes of that inside integral, keep in mind x is a constant, right? So it looks like a function, and I guess, by the time it gets into the outside integral, it kind of behaves as a function. But for the purposes of that inside integral that we're plugging into, X is a constant. So this is really just constant bounds again. It's just that they're constants that change later. Anyway. Okay, so the algebra does end up looking a little bit different. So this 1 minus x, for example, you plug it into the antiderivative, and you see that 1 minus x showing up for y. And there's going to be a little bit more algebraic ugliness to deal with. And it is what it is. So just got to crank it out and just, multiply it all out. Try to be careful. Don't go too fast and miss terms, etc. But anyway, everything else is the same. Okay. Alrighty. A real quick observation I want to make about how we developed this integral. How did we get these bounds, y1 and y2? Well, again, here's our picture. Bounds come from certain points that you identify. Those points are on curves that you can identify. Those curves have certain equations, blah, blah, blah. But did you notice, perhaps, all of that happens in the xy plane? Nowhere in that discussion, at any point, did I need to make reference to, how high, and, what's the function doing? What's the integrand doing? Don't care. It just doesn't come up. The bounds on the iterated integrals are entirely determined by the domain. Right? And because of this, I'm actually going to make a major quibble with the picture that I've drawn here. If the bounds only depend on the domain, why didn't I just draw just the domain? The domain's two-dimensional. Right? I established long ago that volume is a double integral of the function whose graph we're looking at. So I know my integrand is f. I don't really need to draw a picture of the volume anymore. Right? So this is the big revelation, and it's tremendously useful. I don't need to draw this hard to draw, hard to visualize, three-dimensional picture. All I need on this picture is what does the domain look like, and then consider certain values or points, curves, etc. All that happens strictly on the domain. So let me show you that same argument again then about how to find the upper bound and the lower bound, just on a much simpler picture. Instead of this great big ugly three-dimensional picture, you could do it all here. Here's our domain. It's this triangle in the xy plane. Same exact triangle. The slices. Okay, well, now, you got to remember, the slices that I'm making here are where x is a constant and y varies all the way across. Okay, well, if I'm looking at just the xy part of that picture, I don't need to draw the height. What I get then is this. That's what my slices look like, capitalizing on the fact that my pictures can now be much simpler. Right? So x goes from 0 to 1. These are, you might say, as seen from above, these are what the slices of bread look like. X goes from 0 to 1. Then, if I want to know the y bounds, for a given one of those slices, for a given fixed value of x, y starts at there and ends at there, which is eventually going to determine these y bounds. Those points are on these two curves. Those curves have equations. Solve for the variable that you're interested in. And there, you get y equals 1 minus x. Here, you get y equals 0. That's the same calculation we did back with the three-dimensional picture. Just, I don't need the three-dimensional part of it. So, for crying out loud, take pity on yourself. Draw the easy picture. It's all you need for finding those bounds. The integrand is obvious anyway. Big convenience. Okay. All right. So with that in mind, let's do a bunch of examples. We've got 11 minutes left. Okay, I already did that one. Okay, so here are our next example. Let's look at volume under a certain graph sitting over a certain region in the XY plane that's bounded by a couple of curves. Okay, so let's one step at a time here. I'm looking at a volume under a graph. We've talked about volumes under graphs already. Volume under a graph is a double integral, which I'm going to rewrite as an iterated integral, and the function whose graph I'm looking at is my integrand. So I don't really need to see a picture of the domain to realize, from the application in question, what my integrand is. Okay. Now, having established my integrand, the only thing remaining that I don't know is what are these bounds. Those bounds are going to be completely determined by the domain, this region in the XY plane that's given to us, bounded by those two curves. And so now, phooey on the integrand, phooey on the three-dimensional picture of volume. I'm just going to draw this region in the XY plane to figure out those bounds. Right? And let's see, okay, so we've got to figure out what this domain looks like. The bounding curves are y equals x squared and y equals 2 minus x squared. Here we go. There's y equals x squared. Here's y equals 2 minus x squared. All right. And now let's start slicing. You have choices about which way to slice it. I'm going to make a certain choice for reasons that we'll talk about later, but I'm going to do my x slicing first. My x slices look like that. Okay. You can see here that my x slices start at where these two curves intersect. Now, a little bit of a geometry problem, algebra problem, however you want to look at it. That point, that is the intersection of those two curves, that's where this is equal to that, and do the ensuing algebra, and you can find that your lower bound is -1. Okay, all right. The last value of x, well, that's where these two curves intersect. Oh, it's the exact same two curves. So I want to know where that intersects that. And again, do the ensuing algebra. And you find x equals +1. Be careful. Don't forget that when you're looking for the lower bound, in this case, you can tell from the picture that x is clearly negative. Whereas for this upper bound, you can tell from the picture, it's right there, you can see that upper bound is positive. So when you take square roots, you got to think through which one do you need. Okay, so I have my x bounds. Cool. Now I'm going to look at a particular value of x. Oh, let's write this down, by the way. X goes from -1 to +1. Here you go. X, -1 to +1. Okay, outside bounds. Now, for the inside bounds, okay. Let's see here. Y, sort of as you go across that slice, y is going to start at that point. So our lower bound is based off of that point, which is on this curve, which has that equation. Solve for y, and conveniently y is already solved for. But notice I'm following the same pattern. The bound is determined by a point. The point is on a certain curve. The curve has an equation. It's always that sequence of connections. Solve for y. Y is x squared. So our lower bound is x squared. Then our upper bound so our upper bound, y keeps going till it gets to this point. So the upper bound is determined by that point, which, is on that curve, which has that equation. Solve for y. Again, lucky break, it's already been solved for. So our upper bound, 2 minus x squared. There you go. Everybody happy? Okay. There's a tendency to get these backwards. There's a tendency to, maybe be thinking about the wrong place. Like if you look sort of over here, then look, x squared is higher. A lot of students feel like, well, x squared is higher, so shouldn't that be the upper bound? But keep in mind, we're not over here. Right? We're looking on these slices, and so you have to be very, very careful and realize, look, the lower bound point is on this curve, and that curve has that equation. So anyway, be careful. Think it through. Okay. Next question. Suppose I want to find another volume. This is a volume that is between two surfaces. And here's the two surfaces. Okay. Volume between two surfaces. Okay, let's go to our picture. Here's the picture. Our first surface is that plane. Our second surface is this paraboloid, you'll recall from chapter 2. So there they are. Okay. I make a geometric argument that there's a non-trivial Riemann sum argument to make here. If I want to interpret this volume as a Riemann sum, how do I slice this volume up? I'm going to view this as a Riemann sum over this shadow down here, if you will. Let's look at this shadow down the xy plane. And the idea is that if I look at any little piece of area in this shadow, I can think about the amount of volume above it. Above, because of course the domain is my shadow, right? And this amount of volume that's in that sort of, that elevated, that suspended French fry up there, sitting up in space, it's going to be height times area. And so the difference, the one function minus the other function, this difference of z coordinates, that's my integrand. Does that make sense to everybody? Now again, be careful. Students very often get the difference backwards. So specifically notice this height is, it's tops out at the point on the plane. So 4 is the upper, and the point on the paraboloid is the bottom there. So it's real easy to look at this picture and think x squared plus y squared minus 4. That's exactly backwards, right? If you look carefully at the actual slices you're adding up, it's clearly 4 minus x squared plus y squared, and you'll see that right here. So there's our Riemann sum argument. And now again, it's down to bounds. The bounds, we don't really need this three-dimensional picture anymore. All of this stuff that happened up there has served its purpose. I just need to understand what's going on in the domain. The domain, of course, is just that disk. All right, so let's draw that disk. Now, we have to think carefully about where that disk came from. Now, you're going to have to use a certain amount of geometric intuition here. There's no way around that. The geometric intuition that you have to use here is that the disk is bounded by this circle. That circle, I appeal to your sense of geometry, that circle is the shadow of the kind of the edge, if you will, kind of the lip of that, where the two surfaces intersect. Right? So the way we're going to find this domain down here is we're going to figure out where these two surfaces intersect. The surfaces intersect where this z coordinate, let me get rid of all this junk down here, where that z coordinate, the distance up to the plane, is equal to the distance up to the parabola. Right? I need, if these surfaces are going to intersect, I need green to equal to blue. Right? That's where they're going to intersect. And so I get x squared plus y squared is equal to 4. Everybody happy? Okay. So this is a disk of radius 2 down in the xy plane. So looking just at that, now again, I don't need my three-dimensional picture anymore. I can slice this up however I want. Doesn't matter. Suit yourself. Here I'm doing my y slicing first. You can see y starts there and goes like that. Easy to see that y starts at negative 2. Y ends at positive 2. And then, looking at a particular value of y, somewhere between negative 2 and positive 2, looking at that value of y, on that value of y, what's the range of values of x? Okay, well, the lower bound is determined by, that point, which is on that curve, which we agreed has this equation. Solve for x. Right? Keep in mind, the reason you solve for x is because I'm trying to find an x bound. So you solve for that x right there. Okay. Likewise for the upper bound. Now again, it's one of these situations where you got to be careful with square roots. The upper bound is determined by that point. That point is on the exact same curve, which has the exact same equation. So to find this upper bound, you're still solving for x. And of course, there's going to be a square root in that calculation, and you just make the appropriate choice. Okay, so we'll stop there for today. We're out of time. There you go. And pick up there next time. All right, see y'all later. Oh, and I have homeworks to return. If y'all will stick around for a moment, I have 2 sets to return.